In the outer reaches of the solar system, beyond the gas giants and the familiar worlds of our celestial neighborhood, lies a dwarf planet that has defied all expectations. Pluto, once dismissed as a frozen inert relic of the early solar system, has revealed itself to be a world of startling complexity and activity. When NASA turned the James Webb Space Telescope toward this distant object, what scientists saw challenged everything they thought they knew. Pluto, it seems, is not just alive. It is a living enigma, a cosmic puzzle that could redefine our understanding of planetary evolution and the limits of habitability itself. You're the reason this search is alive. Thank you for keeping your eyes open. Somewhere out there, between the stars, something is whispering, and we've only just started listening. If this mystery pulls you in, if it makes you feel that quiet chill of curiosity, hit like, subscribe, and drop a comment telling me where you're tuning in from. And if you want to help others hear this signal too, share this video on X, Facebook, Reddit, or even in your private chats. You're not just watching, you're part of the signal. Thank you for being here. At the heart of this mystery is an atmosphere that should not exist, a haze of organic particles that cools and heats the planet in ways never before observed. This atmosphere is leaking into space, painting its largest moon, Charon, with a chemical signature that defies explanation. No other system in the solar system behaves this way, and as researchers race to unravel the secrets of Pluto's enigmatic behavior, they are uncovering clues that could reshape our understanding of how worlds form, evolve, and even harbor the building blocks of life. But Pluto's revelations are just the beginning. As we push the boundaries of our exploration, we find ourselves on the brink of a new era, one where the coldest, most distant corners of the cosmos hold answers to some of humanity's oldest questions. What does it take for a world to be alive? And what can Pluto, a tiny, frozen outpost on the edge of the known, teach us about our own fragile place in the universe? Part 1. Ice and Fire at the Edge of the Solar System. Welcome to the Kuiper Belt, a vast icy graveyard of the early solar system, where ancient remnants of the sun's formation still orbit in the frigid darkness. Among these relics, Pluto stands apart, not just a frozen rock but a world of contradictions. At 322 kilometers across, it is the largest dwarf planet by volume. Yet its size pales in comparison to the mysteries it holds. For decades, Pluto was little more than a blurry dot in our telescopes, a distant curiosity that marked the edge of our known solar system. But everything changed on July 14, 2015, when NASA's New Horizons spacecraft flew past Pluto at a blistering 50,000 kilometers per hour. The images it sent back revealed a world that was anything but dead. Towering mountains of water ice, glaciers of frozen nitrogen, and an atmosphere that, despite its thinness, teemed with chemical activity. Yet, the New Horizons flyby was just a snapshot, a fleeting glimpse of a dynamic system that continues to evolve in ways we are only beginning to understand. To truly unravel Pluto's secrets, we needed something more powerful, something that could see deeper and farther than ever before. That something was the James Webb Space Telescope, and when it turned its gaze toward Pluto, the results were nothing short of astonishing. Part 2. The Haze That Shouldn't Be. Imagine an atmosphere so cold that it hovers on the brink of collapse, yet so active that it churns with complex chemistry. This is Pluto's atmosphere, a thin veil of nitrogen, methane, and carbon monoxide that stretches just 1,600 kilometers above the surface, less than 1% the height of Earth's atmosphere. But within this fragile shell lies a phenomenon that has left scientists reeling, a haze of organic particles that dominates the energy balance of the entire system. In 2017, Xi Jiang proposed a radical idea that Pluto's atmosphere was not controlled by gas molecules but by solid particles suspended high above the surface. These particles, he argued, absorbed sunlight during the day, heating up and radiating that heat away as infrared energy at night. This process, he claimed, was the key to regulating Pluto's atmospheric temperature. It was a bold hypothesis, but one that would remain untested for years, until the arrival of the James Webb Space Telescope. Launched on Christmas Day 2021, the James Webb Space Telescope, JWST, was designed to peer into the farthest reaches of the universe, probing the cosmos at infrared wavelengths with unprecedented sensitivity. For Pluto, this meant the chance to finally test Jiang's hypothesis. Using the telescope's mid-infrared instrument, MAIRI, researchers led by Tanguy Bertrand of the Paris Observatory set out to observe Pluto's atmosphere in detail. What they found was beyond anything they could have imagined. Part 3. A World Revealed. The data from JWST confirmed Jiang's prediction in spectacular fashion. Pluto's atmospheric haze is real, and it is emitting strong mid-infrared radiation exactly as Jiang had predicted. But the discovery goes deeper than just validating a hypothesis. It reveals something fundamental about how Pluto's atmosphere works, and how it defies all conventional understanding. On most planets, gas molecules control the energy balance of the atmosphere. They absorb sunlight, radiate heat, and regulate temperature. But on Pluto, it's the haze particles that dominate this process. These tiny particles, just tens of nanometers across, absorb sunlight and heat up, then radiate that heat away as infrared light. This cooling effect is so powerful that it drops the upper atmosphere to temperatures as low as 203 degrees Celsius, or 70 Kelvin 30 degrees, colder than it would be without the haze. But here's where things get even stranger. The haze doesn't just cool the atmosphere, it also heats it. When the particles absorb extreme ultraviolet light from the sun, they gain energy, transferring some of that energy to gas molecules in the atmosphere. This heating is so effective that it gives molecules like methane enough energy to escape Pluto's gravity entirely, leaking into space at a rate of 1.3 kilograms per second, or roughly 112,000 tons per year. This raises a paradox. How can the haze both heat and cool the atmosphere? The answer, scientists believe, lies in the properties of the particles themselves. Their size, shape, and composition determine whether they absorb or radiate more energy, and these properties are still not fully understood. What is clear, however, is that the haze controls the entire energy balance of Pluto's atmosphere, affecting global temperatures, atmospheric circulation, and even the planet's climate. Part 4. The Chemistry of a Frozen World. Pluto's atmosphere is not just physically active, it is chemically rich. The mid-infrared spectrum captured by JWST revealed a wealth of hydrocarbons, including ethane, acetylene, propyne, and diacetylene. These molecules are the products of methane photochemistry, a process driven by solar ultraviolet light, breaking apart methane molecules and recombining them into more complex compounds. But the spectrum also contained surprises, fluorescent emissions from methane and deuteromethane, indicating that these molecules are being excited by solar radiation in unexpected ways. One of the most intriguing findings was the detection of deuteromethane, a heavy isotope of hydrogen with 1 proton and 1 neutron in its nucleus. The ratio of deuterium to hydrogen, known as the DH ratio, is a marker of the origin and evolution of planetary materials. JWST measured Pluto's DH ratio in acetylene and found it to be 3 times higher than Earth's, suggesting that Pluto's ices formed in an incredibly cold environment, possibly in the outer regions of the solar system, or even in the interstellar medium before the Sun was born. But interpreting this ratio is difficult. The DH ratio can change over time due to atmospheric escape, photochemistry, and other processes. While the data hints at Pluto's icy origins, it also raises new questions about how this distant world has evolved over billions of years. Part 5. The Methane Connection. Pluto's atmosphere is not a closed system. It is constantly leaking material into space, and some of that material is being captured by its largest moon, Charon. About 2.5% of the methane escaping from Pluto's atmosphere ends up on Charon, settling onto its poles and undergoing a chemical transformation driven by sunlight. This process paints Charon's polar regions with a reddish stain, a phenomenon unlike anything else in the solar system. Charon itself is a world of contrasts. Unlike Pluto, it has no atmosphere, and its surface is dominated by water ice mixed with ammonia-based compounds. But its polar regions tell a different story. Here, methane molecules from Pluto are trapped and transformed, forming complex organic compounds that give the poles their distinctive color. This interaction between Pluto and Charon is a unique example of how one world can influence another across vast distances, a cosmic dance of chemistry and gravity. Part 6. A Climate in Flux. Pluto's climate is driven by cycles of sublimation and freezing. Nitrogen, methane, and carbon monoxide ices evaporate from the surface, move through the atmosphere, and condense in different locations. This activity is centered around Sputnik Planitia, a vast, heart-shaped basin filled with nitrogen ice. But Pluto's orbit complicates matters. Highly elliptical, it takes 248 Earth years to complete one orbit around the Sun, and during that time its distance from the Sun varies dramatically, from 30 astronomical units at perihelion to nearly 50 AU at aphelion. This orbital variation affects how much solar energy Pluto receives, and because the haze plays such a central role in the atmosphere's energy balance, its behavior changes with the seasons. But here's the problem. The JWST observations captured Pluto at just one moment in its orbit. We don't yet know how the haze behaves over the full 248-year cycle, or how it will respond as Pluto moves further from the Sun and its atmosphere cools. Part 7. The Collapse Hypothesis. One of the most pressing questions about Pluto's atmosphere is whether it will eventually collapse. Right now, the surface pressure is about 13 microbars, incredibly thin compared to Earth's 1 million microbars. But models predict that as Pluto moves further from the Sun, the atmosphere will cool and condense onto the surface, causing the pressure to drop even lower. In this scenario, the atmosphere could disappear entirely until Pluto swings back toward the Sun again. The haze complicates this picture. If it continues to cool the atmosphere, it could accelerate the collapse. But if the heating effect of the haze becomes more dominant, it could slow or even prevent the collapse from happening. The question is, which process will win out? The answer could determine the fate of Pluto's atmosphere and our ability to study it in the future. Part 8. The surface beneath. While the haze dominates Pluto's atmosphere, it also plays a crucial role on the surface. The organic particles that make up the haze eventually settle onto the ground, contributing to the reddish and brownish colors we see in some regions. This process connects the atmosphere to the surface, creating a cycle of material exchange that shapes Pluto's geology. The JWST observations revealed variations in surface temperature across Pluto and Charon, with thermal light curves showing how heat flux changes during their rotation. By comparing these measurements with thermal models, researchers determined the thermal inertia, emissivity, and temperature of different regions. Thermal inertia, a measure of how quickly a material heats up and cools down, varies depending on the composition of the surface. Areas covered in methane ice, for example, have different thermal properties than those covered in nitrogen ice or dark organic deposits. But the data also revealed something unexpected. The thermal behavior of some regions suggests a layered structure, with mixtures of materials or layers of dark organic compounds covering brighter ice beneath. These dark deposits, known as tholins, are the same organic particles that rain down from the atmosphere, accumulating over time and affecting how the surface absorbs and radiates heat. Part 9. The heart of Pluto. At the center of Pluto's dynamic surface lies Sputnik Planitia, a massive basin filled with nitrogen ice. Shaped like the left half of a heart, it stretches 1,000 kilometers across and several kilometers deep, sitting almost exactly on Pluto's equator. But Sputnik Planitia is more than just a geological feature. It is a window into Pluto's past and possibly its present. The basin's position is not random. It is the result of a process called true polar wander, where a planet or moon reorients itself so that a mass anomaly ends up at a specific location. In Pluto's case, the reorientation was likely driven by tidal forces from Charon. But for this to happen, Sputnik Planitia would need to be heavier than the surrounding terrain, despite being a depression. How is this possible? One explanation is that the basin is filled with nitrogen ice that is thicker than the crust it replaced, but calculations show that the ice alone is not heavy enough to explain the reorientation. Another possibility is that there is a subsurface ocean beneath Sputnik Planitia. If the impact that created the basin thinned the ice shell, then a liquid ocean underneath would bulge upward, creating the necessary mass anomaly. This hypothesis is tantalizing, but it raises more questions than it answers. Could a subsurface ocean exist on a world as small and cold as Pluto? And if so, what does that mean for our understanding of habitability in the outer solar system? Part 10. The convection. Enigma, Sputnik, Planitia is not a static feature. The nitrogen ice within the basin is convecting, driven by heat from Pluto's interior. Warmer material rises, cooler material sinks, creating a circulation pattern that forms distinct cells across the surface. These cells, roughly 20 to 30 kilometers across, were first observed by New Horizons in 2015, and researchers estimated that the convection cycles take about 500,000 years to complete. But here's the question. Is the convection still happening today? The New Horizons flyby was just a snapshot, and the JWST observations taken 7 to 8 years later are not enough to detect significant changes. but by the time the proposed Pesfani mission arrives at Pluto in 2008, 43 years will have passed since New Horizons. If the convection is happening as fast as the models suggest, Pesfani could detect changes in the pattern, providing direct evidence that Pluto is still geologically active. Part 11. The Composition Conundrum. The mid-infrared spectrum captured by JWST contains a wealth of information about Pluto's atmosphere and surface, but extracting that information is not straightforward. The spectrum is a superposition of multiple components: reflected sunlight from the surface, thermal emission from the surface and atmosphere, and emission from the haze. Separating these components requires careful modelling, and even then, the results are not perfect. Researchers used radiative transfer codes to model how light moves through Pluto's atmosphere, starting with vertical profiles of gas concentrations from photochemical models. These models predict how methane photochemistry produces ethane, acetylene, and other hydrocarbons at different altitudes. But when they compared the results to the JWST spectrum, discrepancies emerged. Ethane abundance matched the models well, but propyne and diacetylene were lower than predicted. Why? One possibility is that the photochemical models are overestimating the production rates of these molecules. Another is that the vertical profiles are different from what the models predict. There's also the possibility of non-thermal effects, where molecules like acetylene are excited by solar radiation in ways that aren't captured by the models. Understanding these discrepancies is critical, as they affect our interpretation of Pluto's chemistry and its evolution over time. Part 12. The Hydrogen Cyanide Mystery. One of the most intriguing molecules tentatively detected in the JWST spectrum is hydrogen cyanide, HCN, a product of nitrogen and methane photochemistry. HCN is interesting for several reasons. First, it is a key intermediate in the production of more complex organic molecules, including amino acids and nucleotide bases, the building blocks of life. Second, it is volatile, meaning it can move between the atmosphere and the surface. If HCN is condensing onto the surface, it could be accumulating in cold traps, similar to water ice in the permanently shadowed craters on the Moon. But the detection of HCN is tentative. Its spectral signature is weak and overlaps with other features, making it difficult to confirm. If it is present, however, it could provide insights into the origin of Pluto's volatiles. Did Pluto's nitrogen and carbon come from the same source, or did they come from different sources and mix together later? These are fundamental questions about how Pluto formed, and HCN could provide part of the answer. Part 13. The Upper Limits. The JWST spectrum also provided upper limits on several molecules that were not detected, including ethylene, propane, benzene, cyanoacetylene, and carbon dioxide. Upper limits are useful because they constrain the chemistry. If a molecule is expected to be present but isn't detected, it tells us something about the processes that produce or destroy it. Take ethylene, for example. Ethylene is a product of methane photochemistry and should be present in Pluto's atmosphere. But the JWST spectrum didn't show a clear detection, suggesting that ethylene is present at lower concentrations than expected, or is being converted into other molecules faster than it is being produced. Benzene is another interesting case. This ring-shaped molecule is a common product of hydrocarbon chemistry and has been detected in Titan's atmosphere. On Pluto, benzene is expected to form through reactions involving acetylene and other small hydrocarbons, but JWST didn't detect it. One possible explanation is that benzene is condensing out of the atmosphere and freezing onto the haze particles, making it a major component of the haze despite being undetectable in the gas phase. Part 14. The Titan Connection. Pluto's atmosphere has often been compared to that of Titan, Saturn's largest moon. Both are dominated by nitrogen and methane, and both have extensive hazes formed by photochemistry. But the JWST observations highlight important differences. Titan's atmosphere is much denser, with a surface pressure of 1.5 bars, about 50% higher than Earth's. Pluto's surface pressure, by contrast, is just 13 microbars. This difference affects the chemistry. On Titan, molecules collide frequently, driving certain types of reactions. On Pluto, collisions are much rarer, so different reactions dominate. The haze composition is also different. Titan's haze is rich in nitrogen-bearing organics, while Pluto's haze appears to be richer in hydrocarbon ices. These differences likely come down to temperature and pressure. Titan's surface temperature is around 94 Kelvin, while Pluto's ranges from 35 to 55 Kelvin, depending on location and season. This 40 to 60 Kelvin difference affects which molecules can exist as gases and which condense into solids. Despite these differences, studying Pluto helps us understand Titan. The two worlds represent different regimes of nitrogen-methane photochemistry, and by comparing them, we can identify which processes are universal and which depend on specific conditions. This comparison extends beyond our solar system. Exoplanets with nitrogen-rich atmospheres and hydrocarbon hazes may exist around other stars, and understanding how such atmospheres work is important for interpreting observations of those distant worlds. Part 15. The Earth Connection. Pluto's atmosphere may also hold clues to the early history of our own planet. Before oxygen became abundant in Earth's atmosphere, our planet may have looked very different from the sky. About 2.4 billion years ago, Earth underwent a transformation known as the Great Oxidation Event, when photosynthetic organisms began producing oxygen as a waste product. But before that, Earth's atmosphere was reducing rather than oxidizing, dominated by nitrogen with smaller amounts of methane, carbon dioxide and other gases. Some researchers believe that early Earth may have had a haze layer similar to the hazes we see on Pluto and Titan today. This haze would have formed through photochemistry, with solar ultraviolet light breaking apart methane molecules in the upper atmosphere and the fragments recombining into more complex hydrocarbons. These would form tiny particles that scattered sunlight, creating a haze. If early Earth did have such a haze, it would have affected the climate, absorbing ultraviolet light and protecting the surface from harmful radiation, but also scattering visible light and cooling the surface. The balance between heating and cooling on Pluto could provide insights into how early Earth's atmosphere behaved. By studying Pluto's haze in detail, we can learn how organic hazes behave in nitrogen-rich atmospheres, and that knowledge can inform our models of early Earth. There's also a connection to the origin of life. The organic molecules produced in Pluto's atmosphere are similar to the molecules that may have contributed to the origin of life on Earth, and studying Pluto's organic chemistry could help us understand the chemical pathways that led from simple gases to the first living organism. Part 16. The Future of Pluto. The JWST observations have answered some questions about Pluto, But they have raised many more. One of the biggest unknowns is how Pluto's atmosphere changes over its 248-year orbit. The JWST data captured a snapshot in time, but Pluto's distance from the Sun, and therefore the amount of solar energy it receives, varies dramatically over that orbit. As Pluto moves further from the Sun, the atmosphere is expected to cool and eventually collapse, but we don't know exactly when this will happen or how the haze will behave as the atmosphere thins. Another unknown is the exact composition of the haze. The JWST spectrum shows emission peaks that indicate the presence of specific molecules, but interpreting those peaks is difficult. Different molecules and molecular structures can produce similar spectral features, and researchers are working on detailed models to match the observations. But it will take time to pin down the exact composition. There's also the question of how the haze affects Pluto's surface. The organic particles that settle onto the surface accumulate over time, but we don't know how quickly they accumulate or how they interact with the surface ices. Do they mix with the ices? Do they form a distinct layer on top? How do they affect the albedo and thermal properties of the surface? These details matter because they determine how Pluto's surface evolves over time. Part 17. The Pesfani Mission. To answer these questions, we need to go back to Pluto. A concept mission called Pesfani has been proposed, which would send an orbiter to the Pluto system, where it would spend 3 Earth years studying Pluto, Charon, and the smaller moons. The mission would launch in 2031 and arrive at Pluto in 2008 using a combination of radioisotope electric propulsion and a Jupiter gravity assist. Along the way, it would encounter 1 or 2 other Kuiper Belt objects, giving us a broader look at this distant region of the solar system. Pesfani would carry 11 instruments, including high-resolution imagers and spectrometers, to map the surfaces and atmospheres, a mass spectrometer to directly measure the composition of Pluto's atmosphere, an altimeter and radar sounder to probe the internal structure, and a magnetometer and plasma spectrometer to study the magnetic field environment. One of the mission's primary goals is to determine whether Pluto has a subsurface ocean, a possibility hinted at by the New Horizons data. If a subsurface ocean exists, it would show up as a gravity anomaly beneath Sputnik Planitia, and Pesfani could map this anomaly by tracking the spacecraft's motion as it orbits Pluto. But Pesfani is still just a concept. It hasn't been approved for development, and even if it were, it wouldn't arrive at Pluto until 2008, 33 years from now. The thermal light curves captured by JWST's MIRI instrument revealed something unexpected about how heat moves across Pluto's surface. When a planetary body rotates, different regions face the Sun at different times, and by measuring how the thermal emission changes during rotation, scientists can learn about the thermal properties of the surface. On Pluto, the light curves showed variations that didn't quite match the predictions, suggesting that the surface composition varies in complex ways. Part 18. The Final Countdown. As we stand on the brink of a new era of exploration, Pluto beckons us with its mysteries. This distant, frozen world is more than just a curiosity. It is a laboratory for understanding the limits of planetary evolution and the conditions that may have given rise to life itself. From its enigmatic haze to its dynamic surface, Pluto challenges us to rethink what it means for a world to be alive. The James Webb Space Telescope has given us a glimpse of Pluto's secrets, but to truly unlock them, we must return. The Pesfani mission, if approved, could provide the answers we seek, but it is decades away. In the meantime, Pluto will continue to orbit in the icy darkness of the Kuiper Belt, its atmosphere churning with